I'd like to start the hearing by calling on the presentation from OPG as outlined in CMD 14H 2.1, 2.1A, and 2.1B. I understand that Mr. Phillips will make this presentation. Please proceed.
Thank you, Mr. Chairman. Members of the Commission, good morning. For the record, my name is Bryce Phillips. I'm the Senior Vice President of Ontario Power's Pickering Nuclear Generating Station. I have with me today on my left Mark Elliott, OPG Chief Nuclear Engineer, and to my right, Kamir Dashtian, Manager of Pickering Public Affairs and Regulatory Affairs. Other representatives of the OPG team are also here to assist in responding to your questions. We are here today to request the removal of the Pickering hold point. We have successfully completed all regulatory requirements and confirmed that the Pickering station remains safe to operate to 2020 with safety margin. In this presentation, OPG will review material we presented March 27th on the fuel channels and on probabilistic safety assessments. We'll present the specific activities we have performed to meet the Commission's requirements on the hold point, and we'll provide some additional comments on a couple of related topics. Let me start first by setting some context. The current power reactor operating license for the Pickering station was granted on August 9th of last year for a 5-year period until 2018. As you know, the license has a hold point that requires OPG obtain the approval of the Commission for operating our pressure tubes beyond 210,000 effective full power hours. The hold point required OPG to complete outstanding confirmatory assessments for the pressure tubes, perform probabilistic safety assessment analysis and methodology development, and to provide an update on the way forward on filtered containment venting as part of future enhancements provided by the Fukushima Action Plan. In this presentation, I will be informing the Commission on the actions that we have completed in order to obtain your approval for removal of the hold point. The hold point on pressure tubes was introduced into the Pickering relicensing because of units 5 and 8 through 8, would eventually surpass the originally assumed design life of the fuel channels of 210,000 effective full power hours within the license period. A lot of work had already been done leading into the relicensing period that demonstrated the continuing safety of the pressure tubes well past 210,000 effective full power hours. But as we approached the relicensing hearings, there were still a few things to be done. CNSC established 8 criteria for the removal of the hold point related to pressure tubes. I will briefly go over the steps that OPG has taken to ensure that the pressure tubes are fit for service and how we ensure that they remain fit for service until the end of the plant's operation. As well, the Commission directed OPG to complete the revised probabilistic safety assessment, or PSA, for Pickering Units 1 and 4 that meet the requirements of the CNSC Regulatory Standard S294. Also to update the PSA for both Pickering Units 1 and 4 and Units 5 through 8, incorporating the enhancements under the Fukushima Action Plan, such as the emergency mitigating equipment. And also to provide a whole-site PSA methodology for the Pickering units. I will outline the work that has been completed in this area and the results of the assessments. OPG was also directed to provide an update on our analysis and way forward for the future enhancements to protect containment through the Fukushima action items. And so I will be updating the Commission on our conclusions. And while this is not part of the hold point, I will also be taking the opportunity to update the Commission on the production of the Emergency Management Public Information document required to be produced by the end of June of this year. Now, before I get into the details of how we have met the Commission's requirements, I would like to say a few words about my personal commitment to nuclear safety. I would not run the Pickering stations, and I would not be here in front of you today if I was not completely satisfied that Pickering is safe to operate. The plant is safe, and I will continue to ensure it is safe. So how do I do this? I'm going to tell you about some of the many tools I have at my disposal, the processes we have established over many years, and the barriers to an event that we have implemented. You've all heard the term defense in depth. You may have sometimes wondered what that means in practicality. Here's a concrete way of looking at it. The entire way the plant is built puts multiple barriers between the radiation in the core and the public outside the fence. The fuel is in ceramic pellets, surrounded by a strong fuel sheath, inside a robust heat transport system, inside a concrete containment structure. I also have reliable process systems to control and monitor the plant, to control and cool the fuel. And then I have independent and redundant safety systems beyond those process systems that can shut down the reactor and cool the fuel. Now, after Fukushima, even if somehow all that failed, I have further emergency mitigating equipment that can be deployed to cool the fuel and power emergency equipment. Now, to run all this, I have detailed and technical and tested procedures, both for normal operation and for emergencies. I have highly trained and certified staff who are continually undergoing training and regular testing to demonstrate their capability. My staff practice for emergency events and training, drills, and exercises. And you may not know this about me, but not too long ago, I was a certified control room shift supervisor, and I was a certified shift manager. This is all managed within a structure that continually promotes nuclear safety and public safety as the culture of how we do things at OPG. And there's continual management oversight of our plant by myself, my directors, and my managers, looking for error-likely situations, looking for risks, looking for things we can do better. We are always striving for excellence. Now today, we're going to talk specifically about a few more of the pieces of OPG's defense in depth and how I know my plant is safe. These include safety analysis, both deterministic and probabilistic. You also probably don't know that I also spent a number of years in the nuclear safety department, performing safety analysis for all 3 stations in this province. So I know something about safety analysis and its significance. And analysis is very important, but it has to be tested against the real world. And that is where our maintenance and inspection programs come in. My staff are doing tests, gathering data, checking that the plant is operating the way it is supposed to. And of course, some things require maintenance, just like your car. Sometimes preventative, and sometimes to fix things that break. Finally, I will add that this isn't just all in-house OPG stuff that we've made up. There are international standards on how we do analysis, how to operate a nuclear power plant, and how to maintain it. And there are Canadian standards that implement them in the Canadian nuclear environment. OPG's programs comply with those standards. And I'll talk about some of them today as I demonstrate how I know my plant is safe to operate. I'm going to start the technical discussion with a reminder that OPG and Bruce Power were before the Commission on March 27th to outline the research and science behind the conclusions on how we know the pressure tubes remain safe. so I'll just briefly summarize the highlights. The originally assumed design life for the pressure tubes of 210,000 effective full power hours was a conservative estimate when the plant was constructed. This number equates to approximately 30 years of operation at 80% capacity factor. It wasn't based upon technical knowledge or experience of the day. We know because we went back and we checked the records. No one had run a CANDU reactor for any significant period of time back then. We know a lot more now than we did then. I referred to international standards a minute ago. Well, we have those and apply those here. There are the IAEA guidelines on how to manage the life cycle of reactor components. This is captured in detail for CANDU reactors in 2 Canadian standards, which are informed by the latest research and by operating experience and real data from reactors and from labs. Extensive industry research has been performed on fuel channels over many years, including the Joint Industry Fuel Channel Management Project. Through this work, I can tell you that all pressure tube aging mechanisms are well known and are within the design limits. A couple of years ago, leading into relicensing, we had a couple more pieces of work to complete. As a result, one of these aging mechanisms related to deuterium ingress into the pressure tube and its impact on fracture toughness past 210,000 hours needed a bit more work and became the original subject of the hold point. What we are going to do in the next few slides is to review some of that research and demonstrate fitness for service past 210,000 effective full power hours. I spoke earlier about multiple barriers. This is shown graphically in this slide and specifically for pressure tubes. This concept applies for all of our barriers. Without getting into all the details, I'll say that the research in question is basically about managing pressure tube condition, detecting possible pressure tube flaws before they become significant, and detecting any leaks before a break occurs. This is a leak before break. So if you note on this slide, ongoing test and monitoring, that ensures we understand our pressure tube aging mechanisms and is used to develop industry standard acceptance criteria. Our fuel channel inspections, that detects for possible flaws, uses industry approved methods to compare to in-reactor conditions to the acceptance criteria. We also have leak detection system. That allows our certified operators to follow their procedures that they're trained and tested to shut down and pressurize the reactor. We spoke to this slide at the March 27th meeting also. Basically, this just illustrates how hydrogen or deuterium ingress into the pressure tubes and its impact on fracture toughness is the key material property that was still being studied in the last 2 years. That research has been done for hydrogen levels far beyond where we are today and enabling us to get to 2020 with safety margin. We have demonstrated our pressure tubes are safe and fit for service to at least 247,000 effective full power hours. The researchers updated fracture toughness model to account for hydrogen levels in the pressure tubes that increase with time. The updated model covers the entire temperature range of plant operation. Hydrogen ingress has little impact on normal operating conditions. That's where the reactor spends the majority of its time. It does make a difference, though, at lower temperatures, during a reactor shutdown or a reactor startup. We have made changes to our operating procedures, training and testing material for these operating conditions. We had independent reviewers, and these reviewers concluded that the updated model is adequate for application in our fuel channel fitness for service assessments. Nonetheless, we are continuing research to further extend our knowledge, to further extend the model, to provide more safety margin. As we described in the March 27th meeting, the first line of defense in preventing a pressure tube failure is avoidance of conditions that allow cracks to develop, and that is the purpose of our inspection program. But we always want to have more than one line of defense. So as a defense in depth measure, we need to be able to demonstrate that for every reactor state, leak before break applies. Now, what's leak before break? Well, we start by postulating a large flaw in the pressure tube and that it starts to leak. We know that this sort of flaw really shouldn't exist, but that's why it's defense in depth. In the likely event that a flaw does exist and it grows into a leak, we have demonstrated the ability to detect that leak. Our annulus gas system provides a highly sensitive leak detection system using both dew point and dew point rate of rise. This provides our certified operators a clear indication, and then they follow their procedures to place the reactor in the safe state, cold and depressurized, before the flaw grows to an unstable size, that is, before the tube breaks. And that's leak before break, and we have that. Now, the authors of the CSA standard, they envisioned that there would be situations where deterministic analysis would not be the optimal way of demonstrating leak before break. So they explicitly wrote in that probabilistic methods could be used as well. They didn't specify how, they just said you could. What we have done is develop that probabilistic method to do this analysis. We needed to complete that work as part of the whole point criteria, and we have done that. But with either method, the objective is still the same: to demonstrate with a degree of reliability, with a high degree of reliability, that if a pressure tube leak occurs, the operator can safely bring the reactor to a safe shutdown state without failure of the pressure tube. And at this point, I should add that the probabilistic LBB evaluation provides enhanced insights into the influence of key parameters related to leak detection capability. And we've reflected those insights into our operating procedures. And that's part of our operator's response to a leak. So we understand hydrogen uptake. The fracture toughness methodology model has been updated and operationalized. We have the probabilistic leak before break, and we provided that information to the CNSC as required. And then we've done an assessment of the whole core using these tools. We've done it for all pressure tubes, for all conditions out into the future, for all units. The assessment shows large safety margins compared to the failure frequency requirements of the standard, all of which confirms that pressure tubes are safe and fit for service. Now, we are aware that our community would like us to publish the fuel channel research results. We will publish summary results, we will publish summary reports similar to what we have done with the PSA. So in summary, on the pressure tubes and 210,000 effective full power hours, all the required assessments have been done and submitted on time. The updated fracture toughness model produces a more conservative envelope in the heat up and cool down range, and our operating procedures were revised to increase margins in these areas. CSA compliant fuel channel fitness for service inspections are performed every maintenance outage, and fitness for service is accepted by the CNSC for every unit following every planned outage. The R&D results have been used to update the fitness for service methods and have shown that the Pickering fuel channels will remain within the design basis until 2020 plus safety margin. They are safe and fit for service to 247,000 effective full power hours. OPG has met the hold point criteria for fuel channels. This supports our submission to the Commission to remove the hold point. I will now turn the presentation over to Mark Elliott, our Chief Nuclear Engineer, to cover the next area of the hold point on PSA.
Good morning, Commissioners. For the record, I am Mark Elliott, Chief Nuclear Engineer at Ontario Power Generation. On March 27th, the industry was in front of the Commission to provide an overview of probabilistic safety assessment, PSA, in particular how it is used as a tool to assess risk. The presentation covered the concepts of risk and safety goals, an overview of PSA methodology, the different uses of PSA, improvements in PSA methodology, and a whole site perspective on risk assessment. I'm not going to try to cover all that material again, but I would like to highlight a few points. Both Level 1 and Level 2 PSAs are required in order to meet the CNSC standard S294. First, you do a Level 1 PSA for core damage, and then you do a Level 2 to consider the impact of containment impairments that can lead to radioactive release. By current industry and international practice, the PSA results for severe core damage frequency and large release frequency are expressed on a per unit basis. That is, the focus is on what happens to a single reactor unit, and the metric is occurrences per reactor year. Multi-unit effects are considered in this process. For example, in a common mode event such as a station blackout, where all units are simultaneously affected by the same initiating event, the total release from all units is considered in the LRF, large release frequency calculation. So the per unit LRF actually captures a mixture of contributions from purely single unit events as well as multi-unit events due to common mode scenarios. Lastly, the PSAs include both internal and external events. That is, events that originate inside the plant, such as a loss of coolant accident, as well as those originating outside of the plant, such as high winds. There are separate PSAs for each of these different types of hazards: a PSA for internal events, a PSA for seismic, fire, flood, high winds, and so on. One of the reasons for having separate PSAs is that for any PSA, any given PSA, we are looking for insights on nuclear safety. Different insights may be gained from each of the different PSAs, depending on the type of hazard analyzed. Hence, it is important to look at them separately. This is a simplified depiction of the safety goals framework under development at the IAEA to show where PSA fits into the safety framework. PSA is one tool that assists in our assessment of safety towards the goal of protection of the public. The foundation of nuclear safety is built on defense in depth principles and the achievement of specific safety goals. This can be expressed in a simplified form as shown on the slide. At the top level, we have qualitative goals expressed in terms of protection of the public. This would relate to health objectives, such as limiting the probability of fatalities due to radiological releases from nuclear power plant accidents. In the intermediate level, we have semi-qualitative goals that are performance-based and action-oriented. These include the various program activities that the licensees carry out, such as equipment testing and maintenance, staff training and fostering a nuclear safety culture, and emergency response. As we progress down this pyramid, the goals become increasingly more quantitative in nature. At the low level are the specific quantitative goals and criteria that include those associated with safety analysis and PSA. It is through all of these supporting elements collectively that nuclear safety is assured and the high-level health objective is met. PSA is one element of that framework, and it is used to numerically assess the probability and consequence of foreseeable events and compares results against quantitative safety goals. This slide shows how PSA has developed and advanced. PSA started in the 80s and covered internal events only. S-294 was issued and expanded to external events. Now that we are in compliance with S-294, the Commission has asked that we move towards aggregation of hazards and a site-wide PSA. Canada is at the leading edge worldwide in PSA development. This is another slide that we covered on March 27th. The key message is that PSA models are quite large and complex. To give you an idea, in a typical PSA model, there are 165 distinct initiating events that are modeled, such as loss of coolant accidents, steam line breaks, loss of electrical power, loss of service water, etc. 40 nuclear power plant systems are represented, shutdown systems, emergency power systems, and others, with tens of thousands of individual potential failures modeled at the detailed equipment component level, supported by a large database of information on performance gathered from equipment testing and other sources. It is labor-intensive to develop these detailed models. For example, it takes 2 years to create a level 1 PSA model. But one needs this level of detail in order to properly determine the probability of the various sequences of events that can lead to severe core damage. Given the robustness and high degree of defense in depth in nuclear power plants, a series of multiple failures has to occur to progress to a severe accident with releases to the public. PSA is more than just the numbers. The main benefits of PSA are the safety insights gained from the process. PSA provides ongoing benefit during operation through insights into important contributors to risk. And PSA provides insight into the relative benefits of various possible risk mitigation measures. At this point, I'm going to turn the presentation back over to Bryce Phillips to speak to the work we have done to meet CNSC expectations to clear the hold point.
Bryce Phillips for the record. Prior to the license renewal of Pickering in 2013, OPG had already submitted a PSA for Pickering units 5 through 8 compliant with the regulatory standard S-294. Coming out of the licensing hearings, the Commission directed us to complete the Pickering A PSA before the lead Pickering B unit reached 210,000 effective full power hours as a requirement for the Pickering hold point removal. As required, the Pickering units 1 and 4, Pickering A, PSA has been completed in compliance with the CNSC regulatory standard S-294, and all values are better than our safety goal limits. No safety goal limit is exceeded. As another part of the Pickering license hold point, OPG was directed to submit an updated PSA for both Pickering units 1 and 4 and Pickering units 5 to 8 that takes into account the enhancements under our Fukushima Action Plan. The enhancements incorporated into the PSAs were primarily our Phase 1 Emergency Mitigating Equipment, or EME. In addition, lessons learned through the PSA process have been implemented into plant operation. To calculate the risk reduction, changes were made in the PSAs, such as changing the modeling assumptions to better reflect plant operation, as well as use of the EME. This again was industry-leading work. Some Fukushima action items are not yet incorporated into our PSAs. Their safety benefits and PSA risk number reductions are not yet credited. Now, the reason for this is that the methodology does not exist worldwide on how to quantify the benefits of crediting things such as Severe Accident Management Guidelines, SAMG, into PSAs. But we've started work on that. In addition, the benefits of Phase 2 EME are not yet incorporated. With the Fukushima Action Plan enhancements that we could model and credit, the lessons learned from previous PSA work, and these new modeling assumptions being implemented, risk is reduced by a factor of 2 up to 10 times, depending on the scenario. The severe core damage frequency estimates for internal events at power for Pickering units 1 and 4 is approximately a factor of 2 less than the severe core damage frequency estimated in S294 compliant PSA. The estimate for large release frequency is approximately a factor of 3 less than the large release frequency estimated in the S294 compliant PSA. Similarly, for Pickering units 5 through 8, the severe core damage frequency estimates for internal events at power has been reduced by a factor of 5. The estimate for the large release frequency has been reduced by an order of magnitude. So as we expected, the Fukushima work has been a real safety benefit. But we're not standing still with that. OPG has an action plan to further reduce the numbers, which are already below the limits, toward our targets, as per our procedures, as per our belief in continuous improvement, and consistent with our vision of achieving excellence. We're continuing to complete our existing Fukushima action plan. And the action plan will include incorporation of the benefits of Phase 2 EME and SAMG, and using operating experience gained through the recent PSA work and from the Darlington PSA update, as well from improved modeling. In addition, we continue to study ways to incorporate SAMG into our PSA calculations and take credit for benefits there. We have provided this action plan to CNSC staff. We plan to complete the updates to the PSA calculation for those aspects that have the highest impact on risk numbers prior to the next Pickering license renewal submission in 2017. There has been a lot of discussion in the 2013 relicensing hearings and by interveners on whether Pickering's PSA meets the regulatory requirements, whether the results are above the safety limits, and thus whether the plant is safe. So let me be perfectly clear. Pickering is safe. I would not run it otherwise. For our PSA, all requirements under S294 have been met. Our PSA meets industry standards. These standards measure risk per hazard per unit. So too does our PSA, and we meet the limits. International work that we are participating in is ongoing toward development of aggregated risk methodology and multi-unit safety goals, of which Canada and OPG are leaders. Nonetheless, we have gone back and confirmed that there are additional reductions in the numbers that we could have achieved if we had done the simple calculation method. We have done some of that refinement. For example, taking account of the time spent a unit is actually at power versus when it is in an outage. And we removed unnecessary bounding analysis and done the actual analysis. Both of these refinements reduce the number. When we take them into account, the Pickering A large release frequency is 1.05 times 10 to the minus 5. Pardon me, 1.03 times 10 to the minus 5. However, that is still without taking credit for SAMG. When we take credit for SAMG, the number is less than 1 times 10 to the minus 5. And we'll quantify that and formalize it. The final PSA requirement for the hold point was to develop a site-wide PSA methodology for the multi-unit Pickering site. There is currently no standard approach, either nationally or internationally, on how to aggregate risks from different hazards or on safety goals to use for the whole site PSA. OPG is working with the Canadian nuclear industry, the IAEA, and international experts. Multi-unit, all-hazard PSA methodologies are currently under development by the international PSA community. And as we previously mentioned, the IAEA is finalizing guidance on a hierarchical safety goal framework. A can-do owners group joint project is being set up to further develop and apply the whole site PSA methodology. Canada is leading the international community on whole site PSA methodology development. And as Mark Elliott noted a few minutes ago, it's important to note that common mode events that impact the whole site are already included in the per unit PSAs, and these will be properly accounted for in the whole site methodology. Safety goals will need to be derived for a whole site PSA. OPG has provided a concept level whole site PSA methodology to the CNSC. Our committed timeline for first multi-unit site PSA has been provided. Safety goal framework by 2015, risk aggregation studies by 2016, and piloted multi-unit whole site PSA in 2017. Interim results will be available as work progresses, and OPG will provide regular updates on these progression points. So in summary, OPG has met all the requirements established by the Commission for PSA to remove the hold point. PSA methodology has been evolving over many years and is a useful tool to support risk-informed decision-making. The insights gained on potential improvements to plant operation are a major benefit. PSA quantitative safety goals are one part of a hierarchical framework that serves to assure nuclear safety and to manage risk. Post-Fukushima actions have introduced an additional layer of protection, which has resulted in even higher levels of safety. Whole site PSA aims to offer an additional perspective, which is considered prudent and serves the public interest. Significant additional work is necessary to complete an accurate multi-unit whole site PSA methodology. Therefore, in terms of PSA requirements, OPG requests the Commission to remove the hold point. The final aspect of the CNSC requirements to remove the hold point is that the Commission required an update on OPG's analysis and way forward for future enhancements to protect containment through the Fukushima action items. The details have been provided to CNSC staff through our regular Fukushima action plan updates. In brief, Pickering has filtered containment venting capability through exhaust filters for normal operations and through the filtered air discharge system for accident conditions. The existing containment provisions are robust, reliable, and effective for a wide variety of accidents, both design basis and beyond design basis. There are multiple and flexible barriers to prevent or limit a severe event progression using methods already in place. OPG has added additional defense and depth measures to cool the reactors and protect containment during beyond design basis events. EME, which are portable diesel pumps and generators, are in place. SAM-G have been issued. Passive autocatalytic recombiners have been added for hydrogen mitigation. Training, drills, and exercises have been conducted. We are also continuing to pursue enhancements. Phase 2 of the EME project will repower station equipment for long-term core cooling and containment cooling and pressure control. Enhancements to emergency guidelines to further streamline operations will be implemented for multi-unit events and for accidents initiated from low power shutdown conditions. These measures are the most practical improvements as the basic elements are already in place. By combining the planned enhancements with the existing provisions, it solidifies OPG's, it solidifies my confidence in the ability of Pickering containment to protect the public in the event of a beyond design basis accident. Again, in this area, OPG has met the Commission requirements to remove the hold point. I would also like to take this opportunity to update the Commission on the development of a new emergency management public information document, which was required to be completed before the end of June of this year. While the provision of this document was not tied to the removal of the Pickering hold point, we feel that this is an opportune time to update the Commission and the public on this initiative. Over the course of many years, many brochures and information packages have been distributed to Durham residents to educate them on nuclear emergency preparedness. This new document was produced in consultation with the province, the municipalities, and the City of Toronto, and provides the public with information they need to know about our integrated emergency response plans. Focus group research conducted late last year showed us that in general, the public has a low level of awareness of what to do in an unlikely event of an emergency. Our research showed us that there were two reasons. Previous brochures didn't connect with residents. They looked like junk mail, and they were more focused on process rather than what residents really needed to know and what to do. We found that people wanted the information in a package that they would remember and keep. Furthermore, they wanted in a simple language that focused on the things that concern them the most: their kids, their loved ones, their pets. They were not as interested in information that outlined the roles and responsibilities of each emergency organization. In January and February of this year, we worked with our partners to develop written content in line with what we heard from all these focus groups. We asked our ad agency to come up with some design concepts for a brochure that people would remember and keep. We then tested the written content and design concepts with additional focus groups and incorporated their feedback into the flashlight design that you see on this slide. Commissioners, I believe you have copies of the brochure in front of you. Everyone in the focus groups agreed that this design really stood out and they would keep it readily available. I would imagine you would agree with the focus groups. The distribution of this new brochure is in progress. This week is Emergency Preparedness Week. Before I wrap up, I'd like to say a few words about openness and transparency. A number of interveners questioned the extent to which OPG has been open and transparent about the work done on the safety case related to Pickering, continued operation, pressure tube life, and PSA. OPG is committed to earning and maintaining the trust of the public, in particular the residents of the communities in which we operate generating stations. This includes a commitment to sharing information about the safety and operations of our nuclear stations in an open and transparent manner. This is done in many ways, including public meetings, such as the Community Advisory Council, our information center, and our website. OPG provides regular public reports on various aspects of our operations, including safety, operating performance, and environmental impacts and emissions, regulatory reports, and non-routine operating activities through many methods. The CNSC's requirement for public information and disclosure for nuclear facilities is outlined in their guidance document RD 99.3. OPG is fully compliant with this document, which came into effect January 1st of last year. In some cases, our information reports and studies can be of a highly technical nature. So it has been our past practice to endeavor to share information that is understandable by the general public by producing a public summary or synopsis of some technical reports. The Pickering B PSA summary report, posted on our public website prior to the 2013 relicensing hearing, was an example of this. We have followed that up with the new Pickering A PSA summary report and an additional report on the benefits to the PSA from the Fukushima Action Plan. These are also on our website, opg.com. Nonetheless, OPG understands the increased public interest in seeing even detailed technical reports supporting the safe operation of our nuclear power stations. For that reason, we are increasing the number of reports and documentation pertaining to licensing process that will be posted on our public website, opg.com. However, there are occasionally reports that have information in them that contain details that, if released, could potentially compromise the safety and security of the stations. And for example, in-depth safety analysis work that includes detailed descriptions of safety and security systems. Those type of reports will maintain our safety and security. In conclusion, Mr. Chairman and Commissioners, with respect to OPG's request for Commission approval to remove the hold point associated with the Pickering License Condition 16.3, we confirm that all regulatory requirements to remove the hold point for pressure tubes have been completed. The station is safe to operate. The Pickering Units 1 and 4 PSA has been completed in compliance with S294. All values are better than safety goal limits. No safety goal limits are exceeded. The station is safe to operate. The PSA has been updated to account for the enhancements required under the Fukushima Action Plan. This is further evidence the station is safe to operate. A methodology for a whole site PSA has been submitted as well, and a timeline for completion of the first multi-unit PSA has been provided. OPG has provided to CNSC staff a report and path forward on containment protection and filtered venting through our Fukushima Action Plan update. Pickering has containment filtered venting and is making several enhancements which would reduce event progression and improve the protection provided. The station is safe to operate, but we've also an action plan to further reduce risks. In conclusion, we have demonstrated Pickering plant to be safe and fit for service and can be safely operated beyond 210,000 effective full power hours of operation to 247,000 effective full power hours. All the requirements for the removal of the whole point have been met. In fact, we have and continue to meet all regulatory and Canadian standards. We respectfully request the Commission to remove the hold point. Thank you for your attention, and we are available to answer any questions that the Commission may have.
Thank you.